Hi and hello everyone. My name is Daniel Effendi. We are from Group 5. We'll present the medical device that we choose, which is hip implant. So this is our members, Dayusong, Kongjia, Muhammad Faris and Hanis Nabila. So next, what is the importance of the hip joint? Hip joint is the crucial joint in our body. It consists of acetabulum, femoral neck and head of femur. Why is it important? Because it needs to support our upper body weight and allows us to walk and the force of the strong muscles of the hip and leg. The disease that related to our hip joint is osteoarthritis. It can cause intense pain due to stiffening of the joint itself. So, the treatment is using the hip implant because hip implant can perform the same function as the natural one. It also can relieve the pain in the hip area due to multitude of reasons. It also helpful to restore the function of the hip function. And the most important is we need to make sure that materials be biocompatible, resisting heavy stress, opposing low frictional force to sliding and having a low wear rate.
Hi, my name is Deusong. I will be talking about the general properties of material for chosen novel design. First, the design should be highly biocompatible. A material's biocompatibility is defined as the ability of the material to give an appropriate host response in specific application. A total hip replacement is done through a surgical implantation. Human's body might be harmed from a non-biocompatible material. Material which is biocompatible helps minimize inflammatory responses and toxic effects. Problems such as degradation, corrosion, blood clotting, and more will occur if the material is not biocompatible. Therefore, it is crucial for the hip replacement components to have a high biocompatibility material since the hip replacement will be installed into a human's body for a lifetime. Some examples of high biocompatibility metal for total hip replacement are stainless steel, titanium alloys, and cobalt chromium alloy. Examples of high biocompatibility ceramics are zirconia and alumina. Example of high biocompatibility polymers is polyethylene. Besides, there are some alternatives such as coatings. We can use coating techniques to coat only the surface of components that will be in contact with our body to achieve high biocompatibility. The examples for the coatings are titanium oxide, nitride, and zirconium oxide. Next, the device should be bioactive. Bioactive material is a type of material that will produce an active response towards the human body. The examples of bioactive materials are bioglass and bioactive ceramics. For example, bioactive ceramics can induce biological responses to repair damaged tissue. It would be better to have a coating of bioactive material onto the total hip replacement device because it promotes osteoinduction better. Osteoinduction is the process of inducing osteogenesis, which is the formation of bone. Therefore, using bioactive material coatings, the residual femoral bone will grow and have a better attachment, especially with the femoral stem of the total hip replacement device. Moreover, we should design the total hip replacement device with a porous coating of the femoral stem. The porous coating of femoral stem provides spaces for cells and tissues to grow and interlock themselves with the device. This establishment of bonding of the material is also considered as a bioactive material. Besides, the device should have a high mechanical strength. Mechanical strength is another crucial indication of a novel design. A high mechanical strength material is chosen every time to prevent the device from failing where fracture occurs. The mechanical strength of a material can be evaluated from a few characteristics such as hardness, toughness, ductility, strength, stiffness, tensile strength, and more. Metal is typically stronger and ductile, therefore suitable to be made into femoral stem. The examples of high mechanical strength metals are titanium and aluminium. Generally, ceramics are stronger than metal in terms of compressive strength and larger elastic modulus. Therefore, ceramics are useful to be made into femoral head to absorb shock. In addition, the device should have high wear resistance. Wear resistance is the resistance of the material against damage physically over time. The ball and socket joint of the hip will produce friction while walking and running. Ceramics are used to make the femoral head because ceramics have a high wear resistance than metals. It can withstand cycling loading due to the body weight better. Besides, ceramics have a smoother surface than metal, which results in low friction when movements are made, therefore less damage. Lastly, the device should be non-magnetic. For example, the material that is non-magnetic or paramagnetic is titanium. If a magnetic device is implanted into our body, it will interfere the scanning result of MRI, and this will cause the surgeons cannot observe the position of the device clearly. To conclude, the general properties of material for our chosen novel design will be high biocompatibility, bioactive, high mechanical strength, high wear resistance, and non-magnetic. Thank you.
Hi, my name is Faris Izwan, so I will present about the conceptual design sketch. Based on the sketch here, his hip replacement consists of two parts: the acetabular cup, which consists of the shell and liner, and the other one is a femoral component, which can be divided into head, neck, and stem. So for the acetabular cup, it is a component which is placed into the acetabulum, which is hip socket. So the cartilage and bone are removed from this acetabulum. Then the acetabular cup will replace this cartilage and bone and attach to the acetabulum by using bone cement or either without cement, based on its type. So basically, there are two types of acetabular cup, which is monoblock cup and modular cup. So monoblock cup is consists of shell with compressed molded liner, and this cup do not rely on a locking mechanism to hold a liner in place. As for the modular cup, it consists of two pieces, a shell and a liner, and the outside shell has a porous coating, while the inside contains a locking mechanism designed to accept lining. So this porous coating used to form a friction to fit the to mimic the trabecular of cancellous bone, and permanent fixation is achieved as the bone grows into the porous coating, and screws can be used together to lag the cup to the bone and providing even more fixation. So we can see here that the monoblock cup and the modular cup is definitely contrast from each other. So for femoral component, it is the component that fits into the femur, our thigh bone, and the bone is removed while the femur is shaped into suitable shape to accept the femoral stem with the attached femoral head. And basically there are two types of fixation, which is cemented and the cementless. So for the cemented implant, we use the acrylic bone cement to form a mantle between the implant and the bone. So while for the uncemented implant, we use friction, shape, and surface coating to stimulate bone for remodel and bone to the implant. So in the sense of implanting and manufacturing, there are currently two types of prosthesis, which is known as monolithic, which is meant from a single part, and also modular, the prosthesis that made of two or more parts. Modular components are usually assembled during the surgery itself, thus enabling the adjusting for implants during future surgical revision. This is big advantage in sense of that the only part of the prosthesis where failure occur can be replaced. So for example, is it possible to replace a worn out polyethylene without removing the other metal part of prosthesis from the bone? So however, the monolithic component is also have advantage. So apart from the cheaper price, in fact that they are less prone to the corrosion and also loosening.
Hi, I'm Jae, and I will discuss about the general material used in hip implantation and also the material chosen for our hip implantation design. The general material used to make hip implantation components are as follows. For the vestibular cup, is usually made by metal or ceramic or polymer, while the liner is made out of ceramic or polyethylene or plastic. The femoral head can be metal or alloy or ceramic, and the femoral stem is composed of metals or alloy. The material chosen to make the vestibular cup and the liner is the ultra-high molecular weight polyethylene. This polyethylene is a thermoplastic polymer due to its extremely long chain with limited or no cross-link. It has high wear resistance, low friction, and high impact strength. Therefore, it has better shock absorption that can minimize the wear effect at the hip joint and increase the durability of the hip implant. For the femoral head, the material chosen is zirconia tufted alumina. This composite material consists of up to 25% weightage of zirconia in an alumina matrix. The addition of a fraction of zirconia to alumina results in a composite material of increased toughness and thus elevate the resistance to the onset of cracking and to crack propagation. This ZTA composite combines the best characteristic of both alumina and zirconia, which is the strength and the toughness of zirconia and the excellent wear resistance, chemical and hydrothermal stability of the alumina. For the femoral stem, the material chosen is titanium aluminum vanadium alloy. This is because of its stiffness is closer to the stiffness of bone and the bone cement. This material has a lower modulus of elasticity, which result in decreased stress shielding and subsequent favorable femoral remodeling. Titanium aluminum vanadium alloy is relatively low toxicity in concentration found clinically, and this material is inert in the physiologic environment. Besides, titanium aluminum vanadium alloy can achieve excellent bone ingrowth into its porous surface.
Now, we move to the degradation of the materials. So, the first material that we choose is ultra-high molecular weight polyethylene. So, the degradation of ultra-high molecular weight polyethylene with gamma sterilization in hair has been associated with decreased longevity of some total joint replacement components. So, in orthopedic field, there are two major problems, which are loosening and osteolysis. So, these problems limit the lifespan of joint replacement. So, with the sterilized by gamma irradiation, this process resulted in the formation of free radicals, which are the precursors of oxidation-induced embrittlement. So the process is the number one. Only in the past decade did radiation cross-linking achieve common diffusion. This process of cross-linking combined with thermal treatment has emerged to increase wear and oxidation resistance of the polymer, and a large number of laboratory and clinical studies indicate positive outcomes. Cross-linking polyethylene is commonly abbreviated as PEX or XLPE, and currently there are different treatments including radiation emitting, irradiation and annealing, sequential irradiation with annealing, irradiation followed by mechanical information, and irradiation and stabilization with vitamin E. So the second material is titanium aluminum alloy. So the titanium and its alloy are potentially prone to hydrogen embrittlement, including this proposed for dental implants. Aluminum corrosion is the gradual decay of aluminum molecules into its oxides that degrades its physical and chemical properties. The last material is zirconia tufted alumina or ZTA. For wear induced by shocks, ZTA is more resistant than alumina in terms of wear volume. ZTA suffers degradation under no aging and 3 hours of artificial aging. For 20 hours of artificial aging, the ultimate duration ZTA seems to show weakness.
Hi, my name is Hansnazia binti Yusuf, and I'm going to continue with the last part, which is the characterization, tools and processes. This is the first machine that we're going to talk about, which is the instrument machine, and we focus on the mechanical characterization. So what is instrument machine? Instrument machine is a displacement control loop frame, which is a standalone, fully digital, single-axis controller that is packaged as a tower. It consists of motor encoder and load cell to collect data, and also it has a static testing system. So instrument machine is used to test the mechanical properties of the materials, where it collects the data by the motor encoder and load cell during the 3 tests, which is the tension test, compression test, and also 3-point bending test. So how this test machine work? First, a load cell is installed in the top of the load frame, and a specimen, which is the test material, is held in place using fixture and grip inside the instrument tower. Once a testing protocol has been initiated, the center cross head will travel vertically propelled by large lead screws located inside the columns. The testing protocol, which has been programmed by the operator beforehand, will determine the speed, distance, and direction of the travel. This is the first test from the instrument machine, which is the tension test. So the first one is during tension test, the material, typically in the shape of the bone can be seen in the picture, is held securely in the jaw of upper and lower wedge grips. In the standard configuration, the upper grip is attached to the load cell, while the lower grip is attached to the fixed base plate of the crosshead. And then the crosshead will move downwards, while the upper grip and load cell will remain statically. And the last one is an extensometer gauge may be clipped to the material cross section to record a more accurate strain measurement that can be seen in the picture above. Next is the compression test. So during the compression test, the material is held in place by a vice grip fixture attached to the base plate of the crosshead. And then the compressive load is applied to the specimen by a platen, and then the crosshead will be moved outward while the platen and the load cell will remain static. This is the last mechanical characterization, which is the 3-point bending test. So during this test, the material is placed across a support cylinder fixture, and a compressive load is applied directly to the center of the material by the loading anvil. Lastly, the crosshead will be moved upward, while the loading anvil and the load cell will remain static. Next, we will focus on the surface characterization, which we will use the scanning electron microscopy, which is SEM. So what is SEM? SEM uses a focused beam of high-energy electrons to generate a variety of signals at the surface of the solid specimens. The signals that derive from electron-sample interaction give information of the material regarding the external morphology, which is the texture of the material, chemical composition, and crystalline structure and orientation of the material. Thus, the image are generated where it displays the detailed and magnified image of the specimen from the data collected over a selected area of the surface of the specimen using a focused beam of high energy of electrons. So SEM contains some essential components, which is the first one is electrode source or electrode gun that generate the electrons. The second one is condenser lenses, which is control the amount of electrons that travel down the column. The third one is the scanning coil, or known as deflection coil. It deflects the beam of electrons. Next, the objective lenses, where it focuses the beam into a spot on the sample. And the secondary electrode detector, or known as SED, it attracts secondary electrons. And the last one is the additional detectors, where it detects the backscatters electron and X-rays. So how this SEM works? First, the electrons will be generated at the electrode source by heating the metallic filament. Next, the electrons will be accelerated and attracted by a knot. And then the electrode beam will follow vertical path through the columns of the microscope and continues to pass through the electromagnetic lens's focus and direct it to the sample. And then the scanning coil controls the position of the beam, and the objective lenses focus the beam into a small spot of the sample. Then, once it hits the sample, other electrons, that is backscatters or secondary electrons, are ejected from the sample. Next, the detectors collected the backscattered electron and convert it to the signal and send the signal to the screen, which it will produce the image. So this is the last part of characterization, where we focus on the chemical characterization using the X-ray diffraction, or known as XRD. So XRD is a technique for qualitative and quantitative analysis for crystalline compounds that will use the information about the position, intensity, width, and shape of diffraction peaks in a pattern of a sample that we can see in the graph below. So XRD is worked by irradiating a material with incident X-rays and measuring the intensities and scattering angles of X-rays that leave the materials. So XRD is used to identify the crystalline phases and orientation and determine the atomic arrangement. It also used to measure the thickness of thin films and multi-layers and determines the structural properties, which is the unicellularity parameters, residual strain, which is the microstrain, grain size of crystallite size and microstrain, epitaxy, texture and orientation, and also the phase composition. So how XRD works? We can see the atoms in a crystal are a periodic arrays of coherent scatterers that can diffract the lights, where this phenomenon known as elastic scattering. The crystal atoms scatter incident X-rays primarily through the interaction with the atom's electron. So these waves cancel each other out through the destructive interference. However, a few specific direction constructive interference occur, which it will satisfy the Bragg equation, which is the 2d sin theta is equal to n lambda. Lastly, the detector detected, process, and count the diffracted rays. That's all from me. Thank you.
Now, we come to the end of our video. So the conclusion that we get is the general materials in our medical device are metal, ceramic, polymer, and alloy. For the properties of the material, we need to know the importance to make the materials be biocompatible, resisting heavy stress, opposing low frictional force to sliding, and having a low wear rate. Last, for the characterization method, the objective is to know important information about the compounds, such as their degree of resistance and reliability of their possible application. So this is our reference, and that's all from our group. Thank you.